keyboard was not working this morning. Not that I was on time to begin with, running late, but it didn't help. And then probably need to sign back into NanoHub. How are things going so far with the last module? Just head nods, nothing coming up yet. Have you had linear algebra before? Has anyone taken it? Oh, really? Okay. This is, I mean, probably if you remember the class, like there's some stuff that is connected, but also this is a lot more like hands-on. Like, how do you solve, like how do you get problems into linear algebra format? Which I feel like linear algebra just assumes like you already did that work. Like someone gave you 10 equations, 10 unknowns, but usually as engineers you have to come up with that first. You have to be able to describe it. Okay. Check in, see what people are kind of coming up with first. Okay, getting started. Yeah. Okay, yeah. What has becomes ill conditioned? Okay. Okay. For that, yeah, the first part. Yeah. Okay. Yeah. Now, shouldn't have any problem. Yeah. Okay. Yeah. Like when you say like here, just solve it. It takes work to like set it up, right? Like, you have to do everything once at a time. Yeah. Yeah, like it's not easy to turn it into a linear algebra problem, but if you can say you can do that. So much easier. Yeah. So last week we were taking a look at like building, or just kind of like the mechanics of like how do you get a matrix into Python. So the array command, every row is going to be in brackets, and every column is now column. I guess this is row 1 inside those brackets, and then you can set an extra bracket to create multiple rows. And we talked about, like, there's one-dimensional arrays, two-dimensional arrays. That's all we're really dealing with here in this class. But you could, one example of like a three-dimensional array would be a picture. Like a picture has, whatever, a small picture might have 100 by 200 pixels. Every pixel location has 3 values. So you'd have like an array of red values, an array of blue values, and then an array of green, all stacked together. So that would be like a three-dimensional array. And then you can get even bigger from there, because you could have like every point in space has a stress state. So now you have a three-dimensional array, but every point inside that 3 dimensions has 3 dimensions with like, or like, I guess that would kind of be 2 dimensions. Yeah, like an array at every point in space. But that's what we're dealing with here. And then I also, where did I do it? Oh, I thought I showed how to use like the diag command. That's okay. All right, I want to take a look at this, because this is like a typical kind of linear engineering problem. So anything that's like steady state or static, like what is the static solution, what's the steady state solution? Usually it's linear algebra. You're like doing some kind of either force balance or energy balance, mass balance, to just say like, what is everything here? And we end up by doing like an energy balance in each room. 3 rooms, 3 equations, so we can have up to 3 unknown mass flow rates. Or sorry, 3 unknown temperatures, sorry. Each room has like some temperature that we're trying to solve for. And what I wanted to show, sometimes like creating, like taking a set of equations and turning it into a linear algebra problem, sometimes that's hard work on itself, on its own. We can augment the method like with some AI, as long as we're kind of checking like what is the work. Has anyone tried this yet? Of like, build me a NumPy array from this set of equations. It's always best to grab like either the HTML or in this case it's Markdown. Oh, I'm trying to highlight everything. So I'm going to copy all that, go into Copilot, haven't been in here for a while for us. But I like to identify like some good spots where you're coming up, in this case, like we came up with an engineering problem. We identified there's 3 unknown temperatures. I know it's a linear algebra problem. So I'm going to have my AI helper help me turn this into so I'm giving AI like the problem, the Markdown problem, and saying like, hey, turn this into like a NumPy array. So specifically, give very specific tasks, like I want NumPy arrays. And let's see how we go. Main things to look out for is sometimes AI doesn't, I use the word know, but it doesn't really know anything. It's just kind of like trying its best like to like pump zeros and ones through things. So take a look at like x. We know we're trying to solve for x. That should be our unknown variable. So t1, 2, and 3. Sometimes it'll also throw in like other values in there. Like it might try to also say that the t in, yeah. Sometimes it tells you like, oh, t in is also a variable we want to solve for. But with 3 equation, you can't solve for 4 unknowns. So it looks, it's giving us some reasoning. It kind of separated out these variables. It created like a right-hand side B matrix, all like pretty print. And now we can look at what it did for NumPy. So let's just copy it in and edit from there. Paste it in. So first step, make sure the all the inputs are what we wanted. 0.1, 12, 0.1, 0.02, 0.02. It looks like it grabbed the equations pretty well, which makes sense. Like we gave it pretty explicit. These are the values. Then the array. Some quick checks that you can do. Is equation 1 only a function of t1 and t2? So I'll scroll back up, and sure enough, I only see a t1 and a t2 in equation 1, and then there should be 2 other terms on my right-hand side, so like that b vector output. So b, here I've got those 2 terms, like a negative q in and that m1 times t in. And then equation 2, I have 3 terms, so it should be a function of t1, t2, and t3. And here, a t1, here's a t3, here's a t2, there's a t2. So there's 2 t2 terms and 1 for each of the t1 and t3. And sure enough, that's what I have here. At least the quick check. And then here, the last equation shouldn't have a t1 in it. T2, a T3, and a T3. Seems like it did what we wanted. But it didn't actually print T, which is kind of weird. And then output, at least for this one, 15.6, 18.5, and 21 in degrees C. And let's check. We have an input of 12 degrees C. We're adding 300 watts of energy in every room. So everything's got to be more than 12 degrees. It's probably not going to be 100 degrees because we are like flowing it and kind of mixing the air. But 15 to 20 kind of makes sense. We have 300 watts of heating and we're kind of cooling it with outside air. So that's kind of like the hands-off, like, I know I have a problem. I know it's linear algebra. AI, turn this set of equations into linear algebra equations for me. Again, here, I would add some units, keep track of here, right? Anything else? quiet today. It is rainy. It's hard to stay motivated. Rain. Let's grab this guy. Just putting like equations in the array so you can kind of see like it should look for the most part the same, but it's a little different because you're kind of organizing into what do I know versus what am I trying to solve for.
Okay. Let's do it in 30 minutes. But I should be done in 2 minutes. Okay. Yeah. It should be seen. Yeah. Process the equations. Yeah. Yeah, sometimes I take FCP, create A, just call it CP times A. Yeah, it's like, 3 by 3.
Oh, there's other drama. Okay.
Yeah, for the most part, like every problem, if you're trying to solve for 3 unknowns, almost always there's 3 equations for like steady state and static kind of problems.
Oh, it's based on T for the array. Okay.
Yeah.
Versus big concerns.
Yeah, exactly. So like T1, 2, and 3 are 3 unknown temperatures.
So that's what we're solving for.
Yep.
Okay, cool.
Less?
So most engineering problems like this, where you're trying to solve for, in this case, 3 unknown values, most of the time you're going to have 3 equations, at least if you're dealing with either energy balance or a force balance. If you're just looking at like static or quasi-static, steady state kind of stuff, then there should only be one answer. We saw in this first problem, you can have like 5 equations, 5 unknowns, but infinite number of solutions, because here you could squish it and move it anywhere you want, as long as the force balance checks out. But those are ill-conditioned problems where you end up with some kind of variation of like 2 plus 2 is x, but then 4 plus 4 is also like 2x. Everyone's getting too good at Python. There's just no questions. I'm just like cranking through. Yeah.
On like the Hilbert matrix one,
Yeah.
in the reading, I just don't understand what the code is doing.
Oh, in the reading?
Yeah.
I'm coming back up to. I'm just running through, so I have everything kind of defined. You mean where we're talking about this one?
Yeah, so why is it in this
This one, like if we're making a 4 by 4 matrix, then we would say n is 4. Then we could just look at the whole H. And then, yeah. That would be a better way to kind of show it, right? It'd be better to change it to match this example, right? And yeah, so if I have that 4 by 4 Hilbert matrix, I can look at the condition, and for the most part, it's like 15,000, 15.5 thousand. So basically like a 10 to the 4 kind of number. And same equation that we're looking at up here. Like if the condition is a 10 to the 4, then its error is going to be a 10 to the 4 minus whatever precision it is. So in this case, for the most part, if you're dealing with these like 64-bit floating point numbers, 10 to the negative 16. So t is 16. So it'd be 4 minus 16. So we have like 10 to the negative 12 accuracy, or like error, expected error. Trying to get it to evaluate it. Kind of this, at least this is what I think of it as. We don't really need the extra. And so you can use this to define like a Hilbert matrix, but there's also built-in Hilbert matrix, like NumPy. Coming down back to the homework and coming here. I think it's from NumPy. No, maybe it's SciPy. There we go. So there's a SciPy, like linear algebra SciPy Hilbert constructor. So if you tell it, I want Hilbert of 10, it'll give you a 10 by 10 Hilbert matrix. And it's the same thing that we just programmed in the reading too, though. And even has an example. By 5.
sort of the accuracy?
That's from that equation of like 10 to the c minus t. So if your condition number is like, if it was on a log scale, like 10 to the c, 10 to the 5, 10 to the 9, and then the t value is where accuracy for single numbers.
So, 10 to the negative 16 is the accuracy. So,
Yes.
the 10 to the number, the matrix.
That's the condition of matrix. Yeah.
So we go through each of them.
Yeah, so each one is going to have its own condition number.
So it's 10 to the condition minus the accuracy.
Yeah.
Equals there.
That's the error. Yeah.
All right, let's do a quick. This is, I know it's like the end of this first reading, but it's the most impressive thing you can say to like applied math people is to check the condition number of their matrix. And like there's a lot of like math and applied math kind of theory behind it, but in general, condition number is like, it's like a temperature test of like, is this a solvable problem? Really high condition numbers are hard to solve. And the smaller the condition number, the easier it is to solve. If you think about, like if we only had a 1-by-1 matrix, like if we say 2x equals 8, then our matrix, our unknown matrix is 2, or sorry, the matrix, our A is just the number 2. So then the inverse of A is 1/2. 2 times 1/2 is 1, and that, so condition number of 1 means it's as solvable as just a 1-by-1 equation, like a single equation, single unknown. Meanwhile, as it gets bigger and bigger, the inverse, either the matrix itself or its inverse, is like becoming infinite. So it could be a really stiff problem, or it could be a problem. I think there's an example up here. No? I thought I plotted. Maybe not. I thought I plotted it. But like the graphical representation is like two lines that intersect at a single point, but they're so close to the same line that it looks like they could have intersected at any point. That's kind of like, if you think about it in a graphic way, that's large condition number. That's what it means. So in the homework, when we're talking about like what is the expected error, what is the accuracy, do you know where this 10 to the negative 16, where that came from? Like why that number? Why not like 10 to the negative 64 bits? Like why not? Do you know where this number is? Or how to find it, like if you're on a new computer? Or someone comes out with like, hey, this is our 128-bit computer, everything's better, accuracy's better. Like what would that number change? I always forget exactly how to do it. Something like that? No. So actually, this one is telling us resolution of like a floating point number. So when you take a number and say like, hey, computer, store this 0.5 for me, it can't store that. Sometimes it can store it exactly. Like 0.5 is the case of a 2 to the negative 1. But 0.51 is like a 2 to the negative 1 plus, I don't know, something else. 2 to the negative 8 plus 2, I don't know, something. You need like a whole bunch of like powers of negative 2 in there. So here this finfo is sort of like, how well can I store information for you? That's what finfo is telling us. So it's telling us the smallest number we could possibly put in there is a negative 10 to the 308 times 1.8, and the biggest is 1.8 times positive 308. So those are like, if we tell the computer store a 2 times 10 to the 308, it'll do its best, but it's probably going to round it back down to this number. Same thing for this resolution, and then also this epsilon. This is the smallest number that you can add to 1 and actually make a difference, which is kind of weird, but it's just a limit of the computer. So let's call this our EPS. So if I take 1 is just the number 1 versus adding EPS to it. Now it's a floating point number and it has some non-zero thing out here. But if I try to say 1 plus EPS over 2, then it's just going to tell me that I have the number 1. So that's where that 10 to the negative 16 is coming from, is that if it's anything smaller than really 10 to the negative 15, it's 0. You can't do anything with it, at least with the number 1. Okay, so let's find like, what is this error? Here, 4.8 times 10 to the 1, 2, 3, 4, 5. And I think I just had a nice format for it, right? So the condition number is roughly 10 to the 5. So error is 5 minus 16, 10 to the 5 minus 16. But it is an upper bound. Like, it's not that every time you use this matrix to solve that, you'll get that error in the result, but it's a very quick way and also a very impressive way. Again, like if you're talking to other engineers, like, hey, check the condition number. And it's a quick check before you start like banging your head against the wall of like, is my code wrong? Are the inputs wrong? It's like, no, it's just an unsolvable problem. Your condition number is like 10 to the 15. So best we could do is like 0.1 error on these results anyway. So keep it in your pocket, condition number. Yeah.
So in the error equation for C, it's just the power of the condition.
Just the power of the condition number. If you want, like it's, and again, this is kind of, it's a ballpark on a log scale. This is accurate. This is so whether it was 1 or 5, 10 to the negative 11, it's kind of 6 of one, half dozen the other. So if you want to know like the actual thing here, we could say, so let's call this C5. So my condition number of that 5 by 5 is this. I could take log 10 of C5 and I get like 5.7, and I could use that as doesn't change it by much. Now it's just like 5 times 10 to the negative 11. It's still on a log scale, like same number. But if you want, you can do that. You could also round it if you want, if you really want to like automate the whole process. Like, what is the floor of this log 10? And then you could look at what is the condition number at any point, right? Now, since I can automate it, again, if you can do it once, you can do it as many times as you want. I'm looking at like what is the expected error as that Hilbert matrix keeps getting bigger. This isn't a general form. Like a bigger matrix does not necessarily mean bigger condition number. It's specifically because the Hilbert matrix keeps getting smaller, so it gets stiffer and stiffer the bigger it gets. Because you start off with a 1, then by the end, you might have like a 1 over 100 or 1 over 50. So it goes up and up and up and up, and then at some point, it just keeps bouncing around that 10 to the 1. And even if we made it bigger, even if we go out to like 30, it's going to keep bouncing around there. Do you know why it's doing this?
Because the numbers are so small.
Yeah. Yeah, so it definitely has to do with like the fact that numbers are getting so small. But it's the round off error. So because, yeah, like in our Hilbert matrix, like numbers are getting so small that when we try to look at the condition, we're just really looking at round off error in this case. So at some point, like when the condition number gets large enough, although we can calculate how much error we expect, it's really kind of irrelevant at that point. Yep. And then we could even look at like what is the condition. Like condition goes up and up and up and then kind of balances off until it's all the same condition number. It's just ill-conditioned. Cool, thanks a lot. And then we'll be back Wednesday and then get a break on Friday.